G'day and welcome to another video on complex numbers. Today we're looking at properties of complex conjugates, and they should be appearing on the screen just next to me now. There's 10 properties there. So today I'm going to prove properties 2, 4, 8, 9 and 10, and then the rest of them I'm going to leave for you as an exercise. So let's start with property 2. Property 2 says that the conjugate of the products is equal to the product of the conjugates. Or in maths, ZW bar is equal to Z bar times W bar. So let's start with proving that. The way we're going to do it is first we're going to define Z is equal to A plus IB and W is equal to C plus ID, two generic complex numbers. And therefore we can easily work out what their conjugates are. Should be appearing on the screen now. So we're going to find the product of Z and W first, which is just expanding brackets, and we'll find the conjugate of that at the end. So the conjugate sign's over the top of the whole thing at the moment. We're just going to leave it there. We're going to find out what the product is first, and then we'll find the conjugate. So that should be appearing step by step in front of us now. Like I said, it's just expanding brackets. And then finally, we'll find the conjugate once we've collected the real parts and imaginary parts. So in this next part, we're going to find out what Z bar times W bar is. Again, it's just going to be expanding brackets, which should be happening now. And look at that, it's exactly the same as ZW bar. So we've proven the result. Property 4 says that Z plus Z bar is equal to twice the real part of Z. Or, writing it another way, the real part of Z is equal to 1/2 of the sum of Z and Z bar. It's that second part that's probably going to be more useful to us in day-to-day life, as you'll see in our very final example of this video. Okay, so again, we're going to define Z is equal to A plus IB, and that means the real part of Z is just equal to A. Well, what is 1/2 of Z plus Z bar? Should be appearing on the screen now. And if we keep simplifying through, collecting like terms, then that whole thing just collapses down to A, which we've already said is the real part of Z. So there's the proof for 4. So 8 is asking us to prove that the argument of Z bar is equal to negative the argument of Z. Okay, and I'm going to do this in two ways. You should be seeing a geometrical proof now. So if we plot Z on the argand plane, then Z bar is just its reflection in the x-axis. There's a 90-degree angle there, so they're always in different quadrants, opposite reflection quadrants, I guess you could say, and the angle there just is theta and negative theta when we're reflecting. So there's a geometrical proof. If we want an algebraic proof, we can do it this way, that the argument of Z by definition is just tan inverse of B and A, and the argument of Z bar then would be the inverse tangent of negative B on A. But since tan is an odd function, then we can pull that negative out and it becomes the negative of arg Z. 9's a real simple one, and again, it's a really important geometric kind of result. We want to prove that ZZ bar is equal to the square of the modulus of Z. So if we define Z to be A plus IB, then recall by definition, the modulus is equal to the square root of A squared plus B squared. So the modulus squared then would be A squared plus B squared. So let's just expand out what Z times Z bar is. Again, it's just expanding brackets. And if we do that and simplify, then we get exactly that, A squared plus B squared, which we've just said that's the modulus squared. And finally for 10, Z to the power of negative 1, we want to say that that's equal to Z bar on the modulus of Z squared. Then let's just expand out Z to the power of negative 1. Well, by definition, that's just 1 on Z. And I can multiply 1 on Z by Z bar and Z bar, because that would just cancel down to 1. And we're using the conjugate here, remember, because that's Z bar over ZZ bar, so the denominator is ZZ bar, and we know that's going to be a real number. If we multiply by a complex number and its conjugate, we're always going to get a real number on the bottom, and that's what we want. But from property 9, we already know that ZZ bar, that's just the modulus of Z squared. So this becomes Z bar on the modulus of Z squared as required. To finish up, we will do an example that's kind of going to go through a whole heap of these different properties. So the example that we're going to go through, you can see here, given complex numbers Z and W, where ZZ bar equals WW bar, Prove that the quotient of their sum and difference is purely imaginary. Sounds daunting. The bit that's going to be important here is unpacking, well, what did that last bit just say? The quotient of their sum and difference. Well, quotient's just a fancy word for a fraction. And we're talking about their sum and difference, their addition and subtraction. So what we want to look at is the fraction z plus w over z minus w. And they're asking us to show that that's purely imaginary. And it might surprise you, but have a think about why this is true for just a second. It might surprise you that the easiest way to attack this is actually to consider the real part of that fraction. So we want to look at RE, or the real part, of z plus w over z minus w. So hopefully you've had a think about that. The reason we want to use the real part is if it's purely imaginary, there is no real part. The real part is 0. So all we need to do to demonstrate this is true is just show that the real part of z plus w over z minus w is equal to 0. So let's set that up. From our definitions, we know that the real part of z plus w over z minus w is just equal to 1/2, and then in brackets that big term, z plus w over z minus w plus z plus w over z minus w conjugate. And then we can use another property to break up that second piece, the z plus w over z minus w conjugate. We can break that up. Instead of the conjugate of a fraction, it's the fraction of the conjugates. So that, in fact, the real part of z plus w over z minus w, we can now simplify it a little bit to be 1/2 of z plus w over z minus w plus z plus w bar over z minus w bar. So we've broken that conjugate fraction into a fraction of conjugates. And now we're just going to get those fractions with the same denominator, which requires a bit of cross multiplication. That's all that's happening in this second step. So we've now got, and I've also brought in that 1/2 to turn it just into one fraction now. And then we have used our result 9 to change that denominator. So instead of having 2 times z minus w times z minus w bar, I've used that result that the product of the complex number and its conjugate is just the square of its modulus. So that's simplified the denominator down nicely now. And now we're going to keep using our rules. So that those bracketed terms, the z minus w bar and the z plus w bar, that's just a subtraction and an addition of conjugates. So we can break it up into pieces. And that's all we've done on the numerator there. Instead of writing z minus w bar, we've changed it to z bar minus w bar. We've broken it up. And we did the same thing for the z plus w conjugate. Now we can just expand those brackets out and simplify. And the great thing is that we're going to end up with a pretty dramatic simplification here. We can cancel out pretty much every term in this expansion, which is nice if you look really carefully. So we're just going to end up with a 0 on the numerator, which is going to give us 0.